For more than 100 years, quantum tunneling has been one of the strangest mysteries in all of physics. A process where tiny particles, like electrons, simply pass through energy barriers they shouldn't be able to cross. It's like watching a ghost walk through a wall. We've known tunneling happens. We've measured where electrons start and where they end up. But what's been missing, the holy grail of tunneling research, is what actually goes on inside the barrier itself. Now, in a groundbreaking experiment, a team of scientists from Pohang University of Science and Technology in Korea and the Max Planck Institute in Germany have finally done it. They've peeked inside the barrier and captured the first ever detailed look at what electrons are really doing during tunneling. Their results don't just tweak our understanding of quantum physics, they reshape it, and could transform the future of quantum technology. This video will break it all down in simple, clear language. What tunneling really is, how this new experiment worked, what the scientists discovered, and why it could change everything from quantum computing to the way we understand the universe itself. Let's start with a quick refresher. In classical physics, if a particle doesn't have enough energy to get over a barrier, it just stops. Think of a skateboarder at the bottom of a ramp. Without enough speed, they can't reach the top. But in quantum physics, particles like electrons don't always play by these rules. Because of the strange, wave-like nature of matter, there's a tiny chance that the particle can appear on the other side of the barrier without ever going over it. That's quantum tunneling. It's like the skateboarder vanishing at the bottom of the ramp and reappearing on the other side without climbing it. Until now, physicists could only measure the before and after of tunneling. We knew where an electron was before it tried to cross. We knew where it showed up after. But inside the barrier, it was a black box. The mathematics of quantum mechanics gave probabilities, but not a clear, direct picture. Did the electron simply vanish and pop up on the other side? Did it interact with anything on the way through? Was it even meaningful to talk about its path at all? For decades, these questions were considered unanswerable because the timescales involved are unimaginably short, attoseconds, or billionths of a second. That's far faster than any traditional equipment could measure. That's where the team led by Professor Dong-Ian Kim at Postec, Pohang University, comes in. Working with collaborators at the Max Planck Institute, they designed an experiment to capture electron dynamics during tunneling in real time. They used ultra-intense, ultra-fast laser pulses so short they last only a few tens of attoseconds, to trigger tunneling in individual atoms. These pulses essentially kick electrons, forcing them to tunnel through an energy barrier. Because the pulses are so fast, they act like a strobe light, freezing the electron's motion frame by frame. By carefully analyzing how the electrons responded to the laser field, the team was able to reconstruct their trajectories, not just before and after the barrier, but inside it. This is the first time any experiment has been able to do this with such clarity. The team named this phenomenon under the barrier recollision, or UBR for short. This is a huge deal, because the conventional picture of tunneling assumes the particle doesn't meaningfully interact with the nucleus until after it emerges. According to that old view, the barrier crossing is essentially passive. But UBR shows that's not the case. Tunneling is a dynamic process. The electron can ricochet off the nucleus while it's still under the barrier, gaining extra energy in the process. This extra energy can then feed into something called Freeman resonance, a special kind of ionization where electrons are much more likely to escape their atomic bonds. Even more surprising, the researchers found that this enhancement in ionization efficiency happened largely independently of the laser field's intensity. That's a direct contradiction to earlier theoretical predictions, which assumed the laser's strength should control the effect. This discovery answers a question that's been open since the early days of quantum mechanics. By showing that tunneling involves active interactions under the barrier, it forces scientists to rethink the models they've been using for decades. It also opens the door to new technologies. If we can control or exploit under the barrier recollision, we might develop better methods for steering electron motion in ultrafast electronics, high harmonic generation, and even quantum computing. Devices based on tunneling could become more efficient or more precise. And on a fundamental level, This experiment gives physicists a rare direct look at what's happening inside one of nature's strangest processes. It's like going from black and white sketches to a full-color photograph. The team's results, published in Physical Review Letters, are just the beginning. Other labs are now preparing to replicate and expand on the work, using even faster lasers and different atomic systems to see how universal UBR really is. If similar effects are found in molecules or solid-state systems, the implications could be enormous. We may be standing at the start of a new era of tunneling research, where what once seemed like a weird quantum glitch becomes a controllable tool for science and technology. Quantum tunneling has always felt like one of the spookiest features of quantum mechanics. Thanks to this breakthrough experiment, that spookiness is finally starting to give way to understanding. If you're fascinated by quantum physics, breakthroughs at the smallest scales, and how they might reshape our world, make sure to subscribe to this channel. Hit the bell so you don't miss our next deep dive into the hidden mysteries of the quantum realm. The story of quantum tunneling